it. So the solution is here. So yeah, the first question says we want to know the film thickness of a fluid with a given velocity. So the fluid is moving at a velocity 5 meters per second in a 3 centimeter pipeline. So we understand that as diameter. And there's a mass transfer coefficient and a diffusivity. So we know quite a lot about this fluid. And then the Schmidt number for this fluid is also known here. So we are told that these correlations are useful. So number one, this correlation applies for this particular fluid. And we want to know what's the flow regime. So clearly we need to know the Reynolds number if we want to know the flow regime. So we need to be able to evaluate this quantity. The second part, what's the film thickness? So the film thickness, of course, is that delta. So in this section on analogies, we had found that we could relate the different types of fluid properties. So the momentum balance could be related to the mass balance, could be related to the energy balance, and that's also a consequence of us knowing that our generalized balance is it has the same form all the time. I don't seem to have that here, but we showed in, I think it's notes 06, the generalized balance. So it has the same form. So that leads us to believe that all these properties are related. And here, if you look at this this equation, it's relating quite different things. So if you think about the Sherwood number is entirely about diffusion. The Reynolds number is entirely about convection. Well, the competition between convection and viscosity. So this is the Reynolds number is very much about the macro properties of the fluid. The Sherwood number is very much about the diffusion and the slow, quiet molecular movements. The Schmidt number is about the competition between viscous drag and diffusivity. So if you like, these are conceptually very different numbers. And it's quite amazing that we can combine them in some way here. So we can actually relate the properties relating to mass transfer to molecular movements. We can relate that to the bulk movements in the fluid and the competition between viscosity and diffusivity. Well, perhaps this one, we do expect to see something like that. But overall, we have this thing which relates quite different properties. And the advantage is that if we have some measurements, then we can exploit those measurements to estimate what's happening in the fluid. Because you see, if you look at the information given here and what we are asked to solve, it's like chalk and cheese, right? We have some stuff about the velocity, but then everything else is about mass transfer coefficients and diffusivity. And you have to think then, this is crazy. This person doesn't realize what they are asking me. How can they only give me mass transfer type parameters and expect me to go and tell them what kind of flow is happening in, what kind of flow regime we have? And it's actually a reasonable request because we have this amazing relationship through the analogies among momentum, heat, and mass transfer. We have a way to relate these fundamentally different types of things. And let's look at how that pans out in the solution. So because we have a Schmidt number, right, we are given that the Schmidt number is 25. And because we have a diffusivity, we can now estimate this ratio mu over rho. So we can estimate the ratio of viscosity to density. Right? We can't get them individually, but you see in the Reynolds number, you don't need them individually. You only need the ratio of viscosity to density. So mu over rho can be obtained directly from the Schmidt number and the diffusivity. And by the way, saying Schmidt number is 25 is not just a cop-out. It's not that yes, it's often the case that we know the Schmidt number. We can characterize for a certain fluid. This is the Schmidt number. So you quite often have available tables of the Schmidt number for particular types of fluids. So you can simply look up a Schmidt number, and then diffusivity. We had a whole section earlier in the lectures on estimating diffusivity. So we can get these two numbers, and it turns out that we can now estimate the ratio of viscosity to density. So if you look in the Reynolds number, du rho over mu, just the standard definition, we can rewrite that as d times u over mu over rho. So we can just rewrite it like that. And then we can recognize here that mu over rho, as we just said here, is Schmidt number times dAb. This should be dAb. So we can estimate the Reynolds number in this way because everything now is given. We are given the diameter and the velocity and the Schmidt number and the diffusivity. So the Reynolds number can be calculated, and then we can use the usual criteria to work out whether the flow is turbulent and so on. Okay, so that's the first part. And then we were asked to calculate the film thickness. Right. So again, that's well, if you look at this data, this seems a bit more reasonable, right? Diffusivity is given, and we know film thickness. If you followed the film theory lecture, you'll know that film thickness is closely related to diffusivity. We know that it's really the competition between velocity and diffusivity that gives us a film thickness. So this one we're not so amazed by, but anyway. So we can calculate the Sherwood number. So the thing is, the film thickness in terms of what relationships we are given, film thickness only shows up in the Sherwood number. So if we can get the Sherwood number, then hopefully we can get. So we know we've got Kc. We are given the mass transfer coefficient, and we are given diffusivity. So if we can get the Sherwood number, then we can get the film thickness. And you can see we've just worked out the Reynolds number. We've just calculated that. And then the Schmidt number is simply given 25. So we can indeed calculate the Sherwood number from this correlation. And so we can get the film thickness. So that's basically the first question. Any questions or comments there? All right. For the second question, we are told that we have a fluid of a given density and viscosity. So in contrast to the earlier case, now we've got density and viscosity. We are given the velocity 2 meters per second and the diameter 3 centimeters. And we are told that Chilton-Colburn can be used. So you've got the J factor, the mass version of the J factor, and the heat version of the J factor. And of course, the Chilton-Colburn analogy is that the factors are equal. And then in terms of the Schmidt and the Prandtl numbers, you've got all the definitions here. So you are given simply the Schmidt number again. See, it's not that different from the earlier one. And then you are told the Dieter's-Butler relationship holds. So that's a famous correlation. It's quite, if you look at what it's saying here, it's quite amazing. I mean, the Nusselt number is related to, where's the Nusselt number? Nusselt, don't have that here. Okay, anyway, we'll see it just now. But yeah, the Nusselt number is related to the Reynolds number. So these do have heat transfer relationships, and now you are getting the influence of convection and so on that. So anyway, we are asked, we didn't read the question yet. We are asked in question 2 whether if you are given this Dieter's-Butler relationship, then can you show that this relationship translates into one of these other ones? And you can see here in the first 2, they are not the same. So Reynolds to the 0.8 and Prandtl to the 1/3. Now you've got Schmidt to the 1/3 over here. Reynolds to the 0.8 is the same, but then you've got Prandtl to the 0.8. This one seems very unlikely, right? Prandtl number is not like a easily translatable to Reynolds number. It's unlikely to be this, but anyway, we'll see that. And so the Schmidt, so instead of Prandtl, we've got Schmidt numbers here. And then in these possibilities, instead of the Nusselt number, we've got the Sherwood number. So we want to figure out which of these four is this one similar to, or is it equivalent to, or can be transformed into. And then once we've got that, the value of diffusivity and mass transfer coefficient. So those weren't given in the problem. So can we estimate which one of these it is? Okay, so let's work through the solution there. So this is just repeating the problem and re-showing the relationships given. So now because JD equals JH, you can just take what JD and JH are and say those are equal. And then just a bit of algebra here, you are just solving for H. So basically, if you just keep H here and divide through by the rest of the stuff, then it looks like this. So you can see Schmidt number and Prandtl number both to the 2/3. So you can write Schmidt number divided by Prandtl number to the 2/3, and then the rest is the same. Notice here your U infinity cancels, right? So U infinity cancels, and the rest is like that. And then if you look back at your Dietrich-Butler relationship, which was this, right? It's just repeated here. Then we can rewrite the Nusselt number here. So Nusselt number, overall heat transfer coefficient, diameter, and conductivity, those ratios. We can replace this H because now we've got an expression for our overall heat transfer coefficient here, right? So we just showed H could be written like this. So you can make that substitution and you end up with that. And then if you, now here's the trick. Well, not a trick. It's not like we're doing something underhanded. Here's a technique, if you like. We are going to multiply and divide by mu times DAB. So we want to try and make some of these other groups, right? And if you just look at what we have currently, you can't really make much out of this stuff. But if you notice here, for example, with that little CP, where your CP needs a mu, and there's no mu over here. So we can just multiply by a mu, and then the other thing we need to do is divide by a k. So you can see you've got dividing by a k. So CP divided by k, and then times mu, then we need to divide by a mu. So we've made mu CP over k, and then we've divided by mu, and then you've got rho DAB. So you can group the rho DAB over there. And then what's left over is that thing. So if you look at this now, you should be able to recognize that we've actually got the Prandtl number divided by the Schmidt number. So this part can be written as Prandtl number divided by Schmidt number. And then you've got Schmidt divided by Prandtl to the 2/3. So Prandtl divided by Prandtl to the 2/3 is going to be Prandtl to the 1/3. So Prandtl to the 1/3. And then Schmidt to the 2/3 divided by Schmidt is going to be 1 over Schmidt to the 1/3. So that's there. And then this thing is nothing but the Sherwood number. So you've got Sherwood number times that. And then you've still got the right-hand side is there. And if you look at this, your Prandtl to the 1/3 can cancel with this Prandtl to the 1/3. And then you can multiply out the Schmidt to the 1/3 here, leaving us with Sherwood equals 0.023 Reynolds to the 0.8 times Schmidt to the 1/3. Right, so the Dietrich-Butler relationship is equivalent to this form, and so that's C in the list of options. Okay, and then the very last bit, we are asked to estimate the diffusivity. Well, you've got the Reynolds number and the Schmidt number given in the problem. So you can, or rather, you are given all this. You are given viscosity and density, and then the Schmidt number. So you can just calculate DAB like that, right? And then we are asked also for the mass transfer coefficient. So the mass transfer coefficient is in the is in the Sherwood number. And now we've just shown that we can calculate the Sherwood number. So we can calculate the Sherwood number using this new correlation. And the Reynolds number is known, the Schmidt number is known, so that's an easy number to get. And then just the Sherwood number is KCD over DAB. We've now calculated DAB, and we are given the diameter of the pipe, so we can calculate KC. Okay, so if you look at it, then D is the correct answer given these numbers. All right, so that's how you can take advantage of analogies and get nice relationships and estimate some